Hi guys, so let's review our mission to Mars activity that we did today. So considering a lander of mass 0.35 kilograms landing on Mars where there is an acceleration of 3.71 meters per second squared. Question 1, and I apologize I don't have a PDF of this, so just follow along on your own worksheet. Question 1, what happens to the velocity of the lander as it falls? Well, the velocity increases as KE increases and PE decreases. Question 2, as the lander falls, which types of energy increase and how do you know? Well, answered above. And the way that you know this is you can observe the lander actually getting faster. Question 3, what force causes the energy from number 2 to increase? Explain why. Or I think in class we changed this question and took out the explain why and calculate the magnitude of the force. So this question is basically asking what causes this shift in energy? What causes the lander to lose potential energy as it descends and pick up kinetic energy? Well, that force that causes that work to be done, or the change in energy, is the gravitational force. And we've always calculated that as mg, right? Weight is the gravitational force. We also call it F sub capital G, or weight on the rover by the planet. So any of these notations is fine as long as you calculate the magnitude correctly. So we're going to say that's equal to the mass, 0.35 kilograms, times the acceleration on the planet of 3.71 meters per second squared. That should give you a quantity of 1.3 newtons. Question 4, which was seemingly complicated. If this force is applied over a distance of 5 meters, how much kinetic energy does the lander gain as it falls? And also, how much potential energy does it lose? So in parentheses, this question says, how does the concept of work apply to this problem? Well, work is going to be equal to the force times the distance times cosine theta, but in our case, the object is moving in the same direction as the force is applied, and so theta is 0. And that's going to be equal to the change in kinetic energy, which is equal to the change in potential. So let's take our 1.3 newtons for force and multiply it by the 5 meters, and we'll get 6.5 joules. So kinetic energy increases by 6.5 joules and potential energy decreases by 6.5 joules, and the work done by the gravitational force, which is the only force acting on the object, is equal to that transfer of 6.5 joules. Okay, the next part of the handout instructs us to consider that the rover starts from rest, and that means that initial velocity is 0. So VI equals 0 meters per second. I know that therefore KE initial is going to be 0 joules, and that's calculated by 1/2 mv squared. Okay, so I'm just going to keep this in my back pocket. I'm not sure yet why the packet is instructing me to know that VI is 0, but I'm just going to remember that for later. So here is our table. The only force that's acting on the rover is the gravitational force. If I were to draw the free body diagram of my rover, I would have my object here, and I would just have weight force on the rover by the planet. Right? There's no normal force. We are not considering air resistance or friction. So there's no non-conservative forces acting on our system. So keeping this in mind, as I read question 1, which helps me to answer the quantities in the table, it says for each of the heights, calculate the magnitude of the force that changes the velocity of the lander as it falls. Well, no matter the delta x, the weight force is going to remain constant, so I know that's going to be my 1.3 newtons. The heights have been pre-populated for you. And question 2 on that same page says, calculate the work done on the lander in each case. Record the work in the table. So I know there was a lot of discussion about how do we calculate MGH and what steps do we follow in order to make this more simple, because I did tell you to think about big picture ideas. And what I want you to think about here to calculate work is that work is equal to F cosine theta D. In our case, theta is 0, so cosine of 0 is 1. And so, apologies, work is just equal to F times D. Okay, so 1.3 newtons times 5 meters is 6.5 joules. 1.3 newtons times 4 meters is 5.2 joules. 1.3 newtons times 3 meters is 3.9 joules. And 1.3 newtons times 1 meter is 1.3 joules. Okay, now question 3 says that if the lander starts from rest, what is the initial kinetic energy of the lander? Well, that's 0. That's what we kind of kept up here in our back pocket. If the rover starts at rest, 0 meters per second, then initial kinetic energy is 0. So in order to calculate our final kinetic energy, I did see quite a few people using the 1/2 mv squared and using VF in that farthest right column in order to do that, which is fine. And you did get some answers that were fairly close to what I had intended you to do. However, recall that in this system where we have no non-conservative forces acting on our system, meaning air resistance and friction, work is equal to the change in energy. So that would be change in kinetic and change in potential. Kinetic energy, or delta KE, is equal to KE final minus KE initial. But recall that this is 0. So we really have work equal to change in energy equal to, and I'm just going to rearrange this so it looks more clear and logical, equal to delta KE. And if delta KE is equal to KEF minus 0, that's just equal to KE final. So that means that the work done is equal to KE final. And I can just copy these over. 6.5 joules, 5.2 joules, I apologize for the bell, 3.9 joules, and 1.3 joules. Okay, so you did not have to do many calculations in order to fill in this table. And that answers question 4 that says using your answers for question 2 and 3. Okay, so the question 4 on that same page instructs you to use the net force and the work in order to calculate the final kinetic energy of the lander. Okay, moving on to the next page. Question 5 says, explain the relationship between final kinetic energy of the lander and the work done. Okay, so question 5 says, explain the relationship between the final kinetic energy of the lander and the work done. So I want to explain this. And I know that those are equal. Since work is equal to delta E, equal to delta KE, equal to KE final minus KE initial, where this is 0 joules. Okay, question 6, draw a graph of the final kinetic energy versus the velocity. Draw a curve of best fit. Don't forget to include label and units. So that I went ahead and did in graphical. Question 7 says, what type of graph would best fit the data? So for 7, I know this is going to be a quadratic fit because I have V being graphed on the x-axis and I have V squared being graphed on the y-axis. That would be the same as saying I've got x on the x-axis and x squared of the function y equals x squared on the y-axis. So I know this is going to be some kind of quadratic shape. So let me go ahead and go over to my graph. And here we go. I see that nice quadratic shape, and I've started with 0 meters per second, resulting in 0 joules of kinetic energy at the origin. And in order to answer question 8, I'm going to take note of the coefficient A in my line of best fit. So see here, I have y equals ax squared plus bx plus c, and my coefficient a is 0.171. Okay, 0.171. So for question 8, ax squared plus bx plus c, where a is 0.171. And the question says, does your graph match the equation for kinetic energy? If so, how can you tell? Well, my formula for kinetic energy, which is on the y-axis, is 1/2 mv squared. So if I'm looking at the relationship between these two equations, where the coefficients of b and c were so small that they approximated 0, okay, so b and c were so small they approximated 0, and I really just have ax squared, and I want to compare that to 1/2 mv squared, where these variables are my independent variables, so x squared and v squared, then a must be approximately 1/2 m if these equations are indeed related. And so a was 0.171, 1/2 of 0.35, okay, and 0.5 times 0.35 is 0.175. So I'm really, really close. So I will consider that proof enough that the graph matches the equation for kinetic energy. Okay, question 9. Question 9 says, suppose the lander had twice the final velocity when it hit the ground. How many times bigger would the final kinetic energy be? Okay, so question 9. Twice the final velocity. So from v to 2v. How many times bigger would the final kinetic energy be? Well, with just v, ke is 1/2 mv squared. With 2v, ke is 1/2 m 2v squared, or 1/2 m 4v squared. So kinetic energy increases by 4 times the amount. Okay, so 4 times. 9b says, how many times higher would the lander need to be dropped from in order to attain this speed? How many times higher would the lander need to be dropped from? Oh, that English just drives me out of my mind. Okay, well, since we're saying that energy is conserved and potential energy or change in PE equals the change in KE, or the potential energy at the very top when KE is 0 equals the kinetic energy at the bottom when PE is 0, then I'm really working with this equation here of mgh equals 1/2 mv squared, where this is the top, where KE is 0, and this is the bottom, where PE is 0. Right, the masses cancel. But if the right side of my equation becomes 4 times larger, so say I multiply the right side by a 4, then I also need to multiply the left side by a 4. Okay, so the answer to 9b is 4 times higher. If kinetic energy was increased by 4 times the amount, then I would need the lander to be 4 times as high so that the left side of my equation equaled the right side. Okay, question 10 says, how would your graphs change if the mass of the lander were doubled? Well, my x-axis was velocity, v final. And this we calculated based on equating energy here to energy there, or energy top to energy bottom, which is mgh at the top equal to 1/2 mv squared at the bottom. So again, the masses will cancel out, multiply by 2, square root the whole thing, and we get velocity equals the square root of 2gh. So notice how the velocity does not depend on mass. So for my x-axis, I would expect no change. But for the y-axis, which is Ke, or 1/2 mvf squared, then if mass is doubled, the kinetic energy is in fact doubled. Okay, so it's like plugging in 1/2 and then 2m vf squared. Okay, so this quantity would double, so it would result in a vertical stretch. Okay, so now we can continue onto the back page, and I'm just going to backtrack a little. So here, this post-investigation check said, rank the kinetic energies of the landers from greatest to least. Okay, I'm just going to make a note to myself since I will forget that. Greatest to least. And I'm going to go ahead and calculate the kinetic energy using only variables for each of these situations. So for A, I have 1/2 mv squared. For B, I have 1/2 2m v squared, or mv squared. In C, I have 1/2 mv squared. In D, I have 1/2 mv squared. And I did hear a couple of you talking about the observation that the velocity changes directions. But remember that energy is not a vector quantity, because even though velocity is a vector, right, we can have positive and negative velocities. Because that quantity is squared, our kinetic energy will always be positive. So we don't need to take into consideration whether velocity is positive or negative. We're comparing the magnitudes of kinetic energy. Here we have 1/2 4m v squared, or 2m v squared. And then for F, 1/2 m v squared, 1/2 m 4v squared, or 2m v squared. So let's go ahead and rank these now from greatest to least. So it looks like our greatest quantities of kinetic energy are, I'm sorry, these aren't lettered for you. Let's go ahead and put the letters in. A, B, C, D, E, F. Okay, so greatest kinetic energies, E equal to F. I apologize for that. Greater than, let's see, B is next. Greater than A, which is equal to C, which is equal to D. Okay guys, sorry that one was a little bit longer, but that was our Mission to Mars worksheet, so make sure you turn this into our class inbox before the end of the week. And that means close of business, COB, Friday. Okay, so this does not mean at 4:30 on Friday after your practice, when I probably will not be on campus. Okay, thanks guys, and I will see you soon.